All right, so chapter 10 is going to cover the dynamics of rotational motion, whereas chapter 9 covered the kinematics of rotational motion, or the description of the rotational motion. Here we'll cover the dynamics of the rotational motion. So the purpose of, or the goals of this chapter, first we're going to introduce torque, study torque a little bit. We'll relate the angular acceleration that we defined in chapter 9. We'll relate this angular acceleration to torque. We'll also talk about rotational work and rotational power. We'll talk about momentum, similar way that we did in chapter 8, but now we'll talk about it in terms of angular momentum. We'll also talk about conservation of momentum, but again, we'll do this in terms of conservation of angular momentum. And we'll also talk about a new way to define equilibrium, in which we involve torque. So we'll add a kind of a second condition of equilibrium, we'll call it. The coverage will cover sections 10.1 through 10.6. So just to kind of get an idea where we're going, sometimes it's good to look back at where you've been. So if we just recap a little bit, chapter 3 was a description of linear motion. Actually, chapters 2 and chapter 3 were descriptions of linear motion. And then we moved into chapters 4 and 5, which were the forces that cause this linear motion. We called those dynamics. That was the branch we called dynamics. Same formulation of our equations is going to hold true between chapters 9 and 10. Chapter 9 was a description of rotational motion. A lot of times we assumed that we had a constant angular acceleration, but we had the description of rotational motion in chapter 9, and now in chapter 10 we'll talk about the forces that cause that rotational motion. So the development of this relationship between between a linear description and a linear cause is going to be very similar to the development of our equations that go from a rotational description to a rotational cause. So the progression of our development of equations should be familiar to you a little bit. So just to get us thinking about what causes rotational motion, let's think about a very simple, quick question here. If you were to push on a door, where would you push on a door to open it? Would you push on the hinge itself? Would you push the farthest you could possibly push from the hinge? Or would you push some distance in between, say halfway between the hinge and the edge? Well, hopefully, if you didn't say you would push on the hinge, because if you push on the hinge itself, then the door is not going to swing open at all, right? So hopefully all of you said that you would push the farthest point from the hinge is the easiest place to open the door, and that's obviously why the doorknob is at the edge of the door, farthest from the hinge, right? So let's talk about why this is. So just as we did with linear motion, we first studied the motion of the rotation, or we will first study the motion of rotation, and then we're going to ask, well, what causes this rotation? Just like we did when we studied linear motion, then we said what causes it. We're doing that with rotational motion as well. Well, we know that motion is caused by a force, right? And a force is a mass times acceleration, right? This is Newton's second law. This is true. This is a law, always true. But we also know that from our study of rotational motion in chapter 9, that linear acceleration of a rotating object depends on how far it is from the axis of rotation, right? We had the linear acceleration, or the tangential acceleration, if you remember back was equal to the radius, or the distance away from the axis of rotation, times the angular acceleration, right? So what two quantities might we expect to be involved in causing some angular acceleration? Knowing that we have F equals ma, we have to have this right here, right? F equals ma, and we also know that this acceleration, this linear acceleration, is going to depend on the distance from the axis of rotation and something else, probably, hopefully you say the angular acceleration of the object. Well, torque is the quantitative measure of the tendency of a force to cause rotational motion about a chosen axis. Or it's basically our force for rotational motion. So it is what causes a rotational motion about a chosen axis. It's the product. We would define it as the product of the force and the moment arm, which we define as a perpendicular distance between the axis and the line of action of the force. This comes from the radius, the distance we have away from the axis of rotation, essentially, that we had when we were talking about a linear acceleration relating to an angular acceleration. This is essentially our r. So we had, before we had a is equal to r alpha. This this L right here is essentially the same as this R right here. It actually is the same length. That's where it comes from. And so torque is that radius times some force, right? So the definition of torque is some force times some moment arm, we call it. And we use this symbol tau, the Greek letter tau, to symbolize torque. The units for it we can see are, well, force is in newtons, length is in meters, so the SI units are Newton meters, and the English units are foot-pounds. It's not in joules. We don't talk about torque in joules. It has the same units, but it's not really an energy. It just happens to be it's a Newton times a meter, so it's Newton meters, but don't ever call torque joules. That's always call it Newton meters or foot-pounds or pound-feet. The sign convention is the same sign convention that we used in chapter 9. It wouldn't make sense to change it up now, right? So if we have a counterclockwise direction is a positive torque, and that's the same as angular position, angular velocity, and angular acceleration. So what do we mean by this moment arm here that we were talking about earlier for defining the torque? We said that the torque is defined as the force applied multiplied by this thing, the moment arm, which we put this equation in the previous slide. Torque is a force times this moment arm L. And we said the moment arm is the perpendicular distance from the point of force application to the pivot point. So we need to know where it's going to rotate, and basically the force is just, or the moment arm is the distance to the force. So let's say we have our axis of rotation is right here, and we have this wrench here, and if I put some force at point A, right, and this is perpendicular, so it's 90 degrees right here. And so when I talk about the perpendicular distance, I mean the distance to the force such that the force is perpendicular. So we have here, it's rotating about this axis. My force is right here. And my moment arm then would be this right here. So my torque created by this force is the magnitude of this force times the distance here, which we call L, this would be my distance, that is the moment arm. I look at the torque created at point B here, and this is this going to be more of a torque or less of a torque? And we go back to the example with the door, and we said torque is a tendency of an object to rotate, right? Or it's what causes an object to rotate. Then, well, knowing that if we push farther on the door, we must be creating a larger torque, right? And we can see that here, this force B, if it's the same magnitude as force C, then I have a much larger moment arm. I'm sorry, not force C, but force B. If force B is the same magnitude as force A here, then the much larger moment arm at force B would create a much larger torque. So this, in fact, is the moment arm for the torque created by force B. Now, the torque has to be perpendicular in order to cause rotation. Remember, it's a perpendicular acceleration that causes rotation, right? A radial acceleration simply causes, this would sort of accelerate this way, right? So a force in this direction wouldn't cause any rotation. It would only cause the wrench to actually slide more towards the nut here, right? Or it would push on the nut that way, but it wouldn't cause any rotation whatsoever. So that's why we say the moment arm is this perpendicular distance from the point of force application. Or we can also say that it has to be the perpendicular component of the force. So this is what we mean. So we have a force applied by some moment arm right here. So force times moment arm gives us the torque, tau, right? So we talked about the units of torque are a Newton meter, right? And we also have the units of work being a Newton meter. And so we might think there's a lot of similarities, and there are some similarities, but there's also some fundamental differences as well. Work causes a change in energy. Actually, torque does as well. But we could talk about work being in joules. We don't talk about torque being in joules. But one of the main differences between work and torque is that work involves a parallel force, and it causes a linear motion, right? So the force is parallel to the motion, it causes linear. It's equal to a change in the mechanical energy. Now, torque, on the other hand, involves a perpendicular force. So the forces are 90 degrees off from each other, and it causes a rotational motion. But does torque also cause a change in rotational energy? And yeah, we'll find out later that it does. If something speeds up more, we'll actually know from kinetic energy of a rotating body from chapter 9 that if it's rotating faster, it has more kinetic energy. And if torque causes an acceleration, then it causes a higher rotational velocity, so it must cause more rotational energy. So there's a lot of similarities and a few differences as well. The major difference is the parallel versus perpendicular. Another key difference between torque and work is that torque depends on how far away the force is applied. The work is applied directly at the object, right? So there's no moment arm involved in work. So it's a key difference between torque and work here. So given our discussion of torque so far and our definition of torque, let's throw up a little quick quiz for you, so you can pause this and try to answer these questions, and we'll come back to it. But if we say this door right here is entirely free to rotate about a hinge. So I have my hinges right here. Here's my doorknob, and I'm going to apply some force at the doorknob, and it's free to rotate. It has some distance r here. This is actually our moment arm L, and it can rotate about this axis through O. And what are the three factors that would determine the effectiveness of the force in opening the door? Hopefully, two of them at least are very obvious. One being the magnitude of the force. The other one being the moment arm, right? That comes from the definition of the torque. If I were to push right here with the same force, then I wouldn't be able to move it nearly as easily. I'd probably actually have to apply a much larger force in order to move it if I'm this far away. And also the angle at which we push would make a difference too, right? If I push like this with the same magnitude F, then not all of it is actually translating to, let me get rid of some of these, not all of it is translating to a perpendicular force, right? So if this is my force F right here, then it would have a parallel as well as a perpendicular component, and only the perpendicular component would cause rotation, right? So the angle would matter as well. So we have here the magnitude of the force, the position of the application of the force, also known as the moment arm, and the angle at which the force is applied. All determine the effectiveness of the force in opening the door. A quick little problem here. So let's say we have this shape that some body in here that's going to rotate about this fixed point right here, and I apply a force over here, force F1 at some distance away, and this perpendicular distance is given by L1. So what's going to be the effect of this force on this body? Well, if it's, say its center of mass is right here, so it's going to rotate about this point, then this force right here and this moment arm right here are going to cause a torque, and which is going to cause a rotational motion, and it's going to cause it around like this, right? You can think, if I have a point here, to find out the direction of rotation of a force, just draw your force here and then put a line there and say, okay, well, it has to be at the top here, so it must be curving down and making a circular path here. So you can say that this is going to be a counterclockwise rotation, right? So I would call that a positive torque. But what would be the magnitude of this torque if the force 1 is equal to 5 newtons and L1 is equal to 30 centimeters? Well, I'll convert this to meters, right? Because torque is in Newton meters. So we have 5 newtons times 0.3 meters, and so we have a torque of 1.5 Newton meters. Now, is there any other motion that's felt by this object other than this rotation? And hopefully you guys haven't forgotten everything that we discussed back in chapter 5, but if there's a force applying over this direction, then it's going to have to cause some acceleration as well, right? So we're actually going to have, not only do we have rotational motion here, but we're also going to have some translational motion here. So it's being translated up that direction, in the direction of the force, right? That comes from, we have F is equal to ma, which is going to give us some translational linear motion of this object, and we'll have a torque is equal to the force times some distance. The moment arm will give us a rotational motion as well. And I apologize for my horrible writing. So a torque is a vector, right? And it has a sign. It has a positive or negative sign. Positive if it's counterclockwise, negative if it's clockwise. If I have a couple forces acting on an object at different, so they're causing different torques, so different moment arms or different magnitudes, then I can add together their torques to find out what the net torque would be, if it's rotating or not. So if we have two or more torques adding or acting on an object, we would add together the torques, making sure that we have our appropriate sign convention, positive for counterclockwise, negative for clockwise. And if the net torque is 0, then we have equilibrium, right? This is sort of, we'll call this a second condition for equilibrium. Our first condition of equilibrium was that the net forces were all equal to 0. Now we have a second condition for equilibrium in which we have the net torque is equal to 0. So if the net torque is 0, the object's rate of rotation does not change. This doesn't mean that it's not already rotating. It's just that the rotation doesn't change. There's just like acceleration meant there was no change in velocity. If there's no angular acceleration, there's no change in the angular velocity. So if there's no net torque, there's no change in angular velocity here. So let's see what we mean by adding all these torques together. And we don't necessarily have to have, all the torques equal to 0. We can still add them up and find out what our net torque is. And if it's non-zero, then we just have some rotational acceleration that's being caused by the net torque, though, right? But we can always add torques together to get a net torque. So let's do a little example here and find out what the torque would be if we have F1, the force 1, is equal to 2 newtons, F2 is equal to 4 newtons. So we have here, this is 2 newtons, F2 is 4 newtons, F3 is 6 newtons. L1, this moment arm 1, is a ½ meter, and moment arm 2 is 0.25 meters. Well, the torque created by F1, first off, we need to say, is that positive or negative? So I look at this here and I say, well, it has to be causing a rotation around like this, right? It's sort of to the right side of it, so it must be going over to the left. So this is going to be a counterclockwise rotation. So this is going to be a positive torque, right? It's a positive torque, F1. F2, however, we look at this and it's down over here, and so it's going to have to wrap around and take some of this stuff out. So this is going to be a positive torque, and F2 is going to wrap around like this, and that's actually going to be a clockwise rotation, so this one is going to be a negative torque. F3, does F3 even cause a torque? Remember, it's the force times the perpendicular distance. What's the perpendicular distance to F3? Well, 0, right? Because F3 runs right through the point. If a force runs right through the axis of rotation, it won't cause any rotational motion whatsoever. It won't cause any torque whatsoever. So we actually say that the torque of F3 is equal to 0. Okay, so this one is 0. So if we sum these up, we'll have F1 will give us a positive torque. We'll say F1 times L1 is going to be 2 times a half, and that's going to be a torque of a positive a positive 1 Newton meter. And just to spare you from having to actually see me write this on the screen like that, we can work out torque F2, or torque 2 created by F2 would be 4 newtons times 0.25 meters. And we said this is going to be a negative torque, right? You have to go in and you have to ask yourself what way is it rotating, and then apply a sign, positive or negative, accordingly. Just like we did with work when we had displacement was either in the same direction or opposite direction as the force, we need to do the same type of analysis with torque as well, because we're not necessarily going to have negative quantities. So we have 4 newtons applied at some moment arm 0.25 meters away, and it causes a clockwise or negative rotation. So this will be a negative 1 newton. This would be a negative 1 newton. This would be a positive or negative 1 newton meter and a positive 1 newton meter. And this will be 0 newton meters. And so our net torque should actually be equal to 0. The sum of all the torques is equal to 0. Well, what if we had, if F1 and F2 both act at 60 degrees off the horizontal, but the moment arms remain the same? So basically, what would happen if these both act 60 degrees off the horizontal, like this, but their moment arms are the same? So essentially, if the moment arms are the same and the forces are the same, we'll still have a summation of torque being equal to 0. But if they're both 60 degrees off the horizontal, like this, then their y components of the force will cancel out. So what actually would happen if we had a scenario like this, where instead of having F1, F2 were in that direction, they were like this? Then would we have rotation? No, we wouldn't have any rotation, because the sum of the torques is still equal to 0. But what we would have is a translation, right? The y component of this force would cancel the y component of this, and I'd only be left with x components. So it would move to the left. The object would move to the left. So of course, force is a vector, right? And torque is a vector as well. And we can break vectors into components. So there's a couple ways that we can actually find torque by breaking either, and actually the moment arm, or R, is also a vector, right? So we can actually break that into components as well. So there's several ways that we can break things into components in order to find a torque acting on something. So let's say I have, this is my axis of rotation right here, and I have some force applied at this point right there, and I want to find the torque created on this rod. This is some sort of lever, and I'm creating a torque on this rod. So I apply some force F up here, and a couple ways I can do it. Well, first off, I know that torque is the perpendicular force, or the force times the perpendicular distance to it, right? So one way we could do it is we could say, all right, I have some angle it's inclined at right here, and I can figure out my angle up here, and I can say I can break this into its component that's perpendicular to the arm here, or the lever, and I can say that my torque would be this radius here, right? The radius of this rotation of the length of the lever times the perpendicular force, right? So I could say that it's F tangent, or F sine of phi, times R. So one way we can find the torque would simply be F sine phi times R, or this is the same as F tangent, the tangential force, times the radius, right? So that's one way by breaking the force into its components, we can find the torque. But similarly, we can actually just break the moment arm into its components as well. I could say, well, that's some distance r, this is some angle phi, then this distance right here, L, is equal to r sine phi. So this gives me a new moment arm. Instead of breaking the force apart, getting a new force, a force tangent, I'll break apart the moment arm and get a new moment arm. And then I can multiply that moment arm by the entire force, right? Because now this is perpendicular, right? So if I did it that way, I'd have, this would be FL, right? Which is actually F times R sine phi, which is actually the exact same thing as F times R sine phi here. So it works out to be the exact same thing. It's just a matter of preference or maybe convenience, which quantity you want to break into its perpendicular component. Would you prefer to break the moment arm into a perpendicular component or the force into its perpendicular component? So just to emphasize, torque is only the force acting perpendicular to the rotation. The radial force does absolutely nothing to add to the torque, right? That'll actually just add tension, which we'll see in chapter 11. It'll add some tensile stress to the arm here, but it won't cause any torque. Only the tangential force will cause torque. We can also derive a relationship between torque and angular acceleration in a pretty straightforward way, based off of the quantities that we developed in chapter 9. So we know that the force that causes a angular acceleration is a force tangent to the path, right? It's this force right here. This is the one that causes our angular acceleration. This does absolutely nothing for an angular acceleration. It's only the tangential force, right? So we can say that the F tangential is mass times the A tangential, right? The tangential acceleration, right? But we know from, and we also know that from the previous slide, that torque is going to be the F tangent or tangential force times the radius, right? That's simply this force times the radius right here. But we also know from chapter 9 that the tangential acceleration is equal to the radius times the angular acceleration. So just making these substitutions, we can actually solve for the torque in terms of actually moment of inertia and alpha as well. So substituting M A tangent in for F tangent, and we'll substitute R alpha in for A tangent. Lots of substitutions here. We'll get a very short and sweet relationship between torque and angular acceleration. So we follow along with the substitution here, but all we really did is substitute F tangent, or actually MA tan in for F tangent, and then R alpha in for A tangent, and we end up with the torque is equal to mr squared alpha. But we also have that, this seems to be out of sync, my animation here, but we also have that moment of inertia is mr squared, right? So this mr squared right here is actually the same as I, so we can say that the torque is actually just the moment of inertia times the angular acceleration. Or if I know a torque, I know a force applied at some distance, and I have some moment of inertia, I can very easily find the angular acceleration. And this is pretty. This is the summation of the torques. Because it's the net torque that we're interested in for our angular acceleration, right? So the sum of torques is equal to the moment of inertia times the angular acceleration. This is analogous to Newton's second law for rotational motion. And this is F equals ma for rotational motion. We have a force corresponds with a torque. So we have force and torque correspond. They're sort of linear. We're making all these analogies to linear motion in chapter 9 and 10. And torque lines up with force. We already know that mass is analogous to moment of inertia, and linear acceleration is analogous to angular acceleration. So we have essentially the same equation here. Put in words, it just says the net torque about a chosen axis. We can actually choose the axis of all the forces acting on a rigid body equals the body's moment of inertia multiplied by its angular acceleration. And remember, moment of inertia is something that it's an inherent property of the body we're dealing with, because it describes how the mass is distributed around the axis of rotation. So it's dependent on the body. It's also dependent on where it's rotating. We also have an analogy to work in rotational motion, or between rotational motion and linear motion. We have the work done in linear motion was the force, the parallel force applied through some distance, right? So there had to be the parallel force, and it was simply a force applied through some distance is our work for linear motion. For rotational motion, we'll just replace the parallel force with the torque and the linear displacement with the angular displacement. The same sort of substitutions we've been making all along, right? Instead of talking about a displacement, a linear displacement, we talk about an angular displacement, so we'll call this some theta. And instead of talking about a force parallel, we'll talk about a torque instead. So making these substitutions, we get our definition. We won't go through the whole derivation of it, but we get our definition of work in rotational motion. So work is equal to torque times the change in angle, or just tau delta theta. Units for this are the same as units for joules at any time. There are units of work at any time. They're in joules. And what does, remember back to chapter 9, what does theta have to be measured in for this to hold true? Hopefully you say that theta has to be measured in radians. If you put in degrees in here, it's not going to work. So SI units are joules. As long as the work is in Newton meters, it's joules. And theta is in radians. This is the only way. It's joules. We also said we were going to talk about power. And power is just a rate at which work is done, right? So power is a change in work with time. Here, this is the same definition we used to define power in chapter 7. And so this is delta W over delta T, the change in work with time. But delta W is actually a tau delta theta, right? A torque times a change in angle. So we have, this is our delta W with time. Then we also know, though, that change in angular position with time is what we defined as the angular velocity before, right? So delta theta over delta t is the same as omega. So power in rotational motion actually simply becomes the torque applied times the angular velocity. Again, note that in order for all this to work, theta has to be in radians for this stuff to hold true. Otherwise, it won't work. Again, so making some linear analogies to rotational motion, we have linear momentum. P is equal to mass times velocity. Sparing the details, but going through the same sort of conclusion, coming to the same conclusion that we came to with the rest of the relationships between linear and angular quantities. You might be thinking, well, maybe angular momentum is then, let's see what I would replace a mass with, I guess moment of inertia. So maybe angular momentum is moment of inertia times velocity gets replaced with angular velocity omega, right? So linear or angular momentum is actually just going to be equal to I omega, and you'd be exactly right. We would have the angular momentum, which we represent with the variable L, is equal to I omega, the moment of inertia times the angular velocity. So L is the angular momentum, and the units here would be, moment of inertia is kilogram meter squared. So and then, kilogram meter squared, and then angular velocity is radians per second. So the SI units are kilogram meter squared per second. Of course, the next thing to do would say, well, we have momentum, we have angular momentum, so we must see if we can have a conservation of that, and we do. We have a conservation law for angular momentum as well, and that conservation law says the same thing that the conservation law for linear momentum said. Basically, that the total angular momentum of an isolated system, so a system that's not having some external forces acting on it, is constant. Or if we wanted to put it up mathematically, we have the initial angular momentum is equal to the final angular momentum. Or we have the initial moment of inertia times final, or initial moment of inertia times initial angular velocity is equal to final moment of inertia times final angular velocity. The interesting thing about the rotational moment of, or rotational angular momentum is that we can actually change both the velocity, the rotational velocity, the angular velocity, but we can also change the moment of inertia pretty easily as well, because moment of inertia is, it describes how the mass is distributed, right? So all we need to do is change the distribution of the mass to get a change in the moment of inertia. This is what a figure skater does when they bring their arms in. If they, let's see here, if we have angular momentum as moment of inertia times angular velocity. If I were to increase one, so let's say I have some constant angular momentum where it's conserved. If I increase my moment of inertia, make this quantity bigger, then I would have to decrease my angular velocity. If I decrease my moment of inertia, then I'm going to increase my angular velocity, right? So a figure skater can make their moment of inertia smaller by simply redistributing their weight closer to their axis, right? So by pulling their arms in, they can actually start spinning faster and faster. And that's the stuff we see with the conservation of angular momentum. Of course, again, all of these, in order for these equations to hold true, theta must be expressed in radians. Finally, we can actually rewrite Newton's second law in terms of angular momentum. Remember, for linear momentum, we said that it is essentially an impulse, right? A change in momentum with time. So making the same sort of analogy for angular momentum, we have the sum of the torques is equal to the change in angular momentum with time. And that wraps us up for the dynamics of rotational motion. Again, stay tuned to La Lima for some example problems.